So the next topic I want to talk about is regression. And the idea of regression is essentially to make predictions of values of a function given an input. So the task is going to be different in that we're going to be mapping now to a continuous space, typically not a discrete set of classes. So classification and regression are both learning functions. The real difference is that classification is learning a function to a discrete set. Regression is learning a function to a continuous set. Okay, so let's consider the case of doing regression in one dimension, and we'll just keep things very simple. We'll be working in the setting typically of the real numbers, so in Rn typically, and we'll start with R1, of course. And so the idea of the regression task is we're going to consider a collection of data that we receive where there was some ground truth function, let's say f, which, when you give f an input xi, which is a feature vector as before, this gives you an output, but what you're going to see as your output that you're going to receive isn't going to just be the ground truth f of xi, but you're going to have f of xi plus some noise, which we'll label as epsilon sub I. So the data pairs that we're going to be getting xi, yi, the output is corrupted a little bit with noise. And we're going to make the assumption that the noise, epsilon sub I here, always is of the nature of being mean zero. Because if it were not mean zero, then we would in fact be considering that part of the function f here. So just to kind of separate out what is the primary signal and what is the noise, this is a very important convention that you'll see throughout all regression tasks. And then we'll assume also that the data that we're given aren't necessarily points xi that we can go out and choose. They're also going to follow some data distribution. So we'll be given a sampling of this function f at random inputs, corrupted a little bit by noise. And then, of course, the task from that is then from those data sample pairs, xi, yi, we'll be given a finite collection of those, typically m. We want to find a model from some hypothesis space so that we can approximately predict what the appropriate value of y is given the input x. And so ideally, what we'd like to do is we'd like to try to have h recover f if f was a member of our hypothesis class. Of course, most of the time we're going to be in an inconsistent setting where we can only get h, to be an approximation of whatever the ground truth f was. So we'll see that that has some implications in how you formulate the regression problem. Okay, so that's the basic regression task, which is to learn a predictor of y from inputs x that mimic the data that we have. Okay, so one of the simplest examples of regression that we're probably very familiar with from various settings, our statistics classes and so on, is linear regression. And the idea there, of course, is you're given a collection of data and the hypothesis space over which you're learning is the class of linear models. Okay, so that's going to be something we can write down mathematically, which is h of x would just be defined by the weight vector w. You dot that with the feature vector, and you add a bias. That's the collection of models which you're referring to and that we work with when we do linear regression. Now, of course, as we know, if we did a nonlinear transformation, we could also kernelize this approach by doing a nonlinear transformation of the data into some new feature space. And as I'll show you later, we can ultimately reduce a lot of the actual optimization, as you guessed, through dual formulations in terms of evaluations of a kernel of xi, xj. Okay, so what that would look like is we're essentially be doing a form of regression where we're linearly combining some collection of features phi of xi. You can even think of phi of xi as being almost like a library of functions. You could think about the w as being kind of a weighting over that library if you used infinite dimensional feature vectors. And then this would be essentially doing a form of nonlinear regression, for example. So just because a lot of the techniques that I'll show you are developed in the linear setting doesn't mean that they don't apply more generally. Through the kernel trick, we can amplify that to solve a lot of interesting nonlinear regression problems. Okay, so linear regression, it's probably the most common form of regression that you'll encounter across a lot of different machine learning tasks. I'll also mention that in these models, it's often not only of interest just to get an h which predicts y well, but it's also of interest the w vector that you get, because in some sense, if w has components which are 0, that would show you that that particular factor, that component, that feature, in the vector x isn't really contributing much to the final prediction. And so that's often helpful because it tells you a little bit about the dependency between the inputs and outputs. And that can be insightful in many situations in which we will use regression to formulate models, such as in econometrics, finance, and also in various machine learning tasks related even to causality. Okay, so this is an example of a kind of typical regression task. You might be given something like the square footage of a house, in this case in Berkeley, and you want to create a model for what the price of that home would be given the square footage, right? So you're given this noisy data, and the simplest thing to do is to create a linear model. And if you do that, it kind of just gives you a way of thinking about how square footage correlates with home prices. And you read in the newspaper all kinds of statistics like what's the average price per square foot of either an office building or a house. This is basically how they come up with those estimates. They do some kind of linear regression of noisy data like this, and then use the W vector. This is a very famous example related to the relationship between sepal length and petal length in a genus, a few flowers, and so there's a few different species, and you can work out a linear model that basically makes a prediction between those two key attributes. That goes back to Ronald Fisher and others. So that's just a few quick examples of linear regression. And now what we want to do with this is formulate a kind of learning framework, just like we did before, so that we can start to extend this into the nonlinear setting, have more flexible types of hypothesis spaces, not just linear models. Think about the various places where we can start to introduce various types of inductive bias, regularizations, information that we may know about the underlying model that we're ultimately trying to discover from the data. Okay, so obviously the key driver in doing regression is going to be your choice of loss function. And so here what I'm showing is the loss function is going to be some map now from our prediction space across the prediction space to the rails, just like before. And the most common loss function that will be used will be the LP loss. And this will just be for two predictions that you're making, y prime and y, it'll just be the usual LP norm. So least squares loss is the one that you're probably most familiar with. And if you look closely, that's just the case of an L2 loss with p equals 2. And we'll use that most commonly. But there's going to be other choices of p that are often desirable for certain problems. We'll see that L1 type losses can be very helpful in areas like compressed density to sort of promote sparsity. And there's just different theory depending on what you're trying to achieve. There's different quality factors to consider in terms of the p-value that you choose. But p1 and 2 will be some of the most common that you'll see arise. Okay, so then just like before, there's going to be the generalization error. This is the thing that we're really trying to optimize when we do a machine learning task. We want ultimately, for whatever the data distribution is, we want our loss function to be small. In some sense, that's by definition what the whole objective is. Find a model H that makes the generalization error small. Of course, the challenge in practice is we only have empirical losses accessible to us. And ultimately, we're going to try to close the gap between the empirical loss and the generalization error. And that's going to be the whole game, is to figure out how to do model selection so that we ultimately can bound RH here using information like had RH here, plus other considerations related to complexity of the model class, regularization, or other considerations. Okay, so that's the kind of setup we had in the classification setting. I'm just showing that there's kind of a mirror setup as well in the case of regression. Okay, so there's going to be a slight technical twist that we need to, or just consideration that we need to be mindful about when we're doing these analyses related to regression, which is that often it's not so convenient to have loss functions which are unbounded, because then it becomes difficult to make certain statements. Basically, what we'd like to do is kind of control the order of magnitude that things are happening on. And so the way we'll typically do that is, even though we will, for practical purposes, essentially just be using an L2 loss, we'll truncate the losses, typically that they have to be less than or equal to some critical value m. But that's primarily done for technical reasons. And so if you see this terminology of it's a bounded regression problem, this is what is being referred to. Okay, so an example would be we might have these squares, but rather than having arbitrarily large losses, at some point we'll just say, hey, if you get an error, it's big. And we'll say We don't care exactly how big it is in terms of the square error. All we know is it's big, and we'll penalize that by this capped amount m. And that reduces some technical issues that come up in some of the proofs and analysis. Okay, so there's many variants of regression, and I'll be telling you about each of these in a little bit. Linear regression, I just kind of walked through the basic idea. There's going to be what's called kernel-ridge regression, which is often very helpful and useful, especially when we introduce kernelization in getting well-posed regression problems, especially when we use feature vectors, which are infinite dimensional through phi, things like RBFs, and I'll show you how that works. And then also we can leverage ideas very closely related to the support vector machines to do something called support vector regression. And we'll see how you can define a notion of margin and not penalize the noisy data too much that's kind of within the margin. And this often becomes helpful for certain machine learning tasks. And then I'll discuss this idea of lasso regression, which has close connections with compressed sensing. And I'll show you how you can use this to do basically image reconstruction. So essentially you can do tomography where we can invert the right-on transform in order to see from measurements of essentially the radon, the average along lines. This would be similar to taking like an X-ray, being able to reconstruct the 3D density, or in this case, the 2D density from that information. I'll show you an application of regression in that context, and it's referred to as the lasso. And the key idea there is going to be to make use of the L1 regularization in order to promote sparsity in the reconstructed solution. And I'll show you some practical examples there about what happens if you use L1 versus L2, what the role of the hyperparameters play in that context. Okay, so that's a really quick outline of kind of some of the forms of regression I'll talk about, and I'll also discuss some other topics. Okay, so let me motivate for you where that least squares problem comes from that is used kind of ubiquitously in regression tasks. And so what I want to do is just kind of show you that some of these ideas, have their basis from, probabilistic thinking in terms of how the statistical errors are behaving. And then once I do the derivation for something you're very familiar with, then I can start to extend it into a context where maybe you're a little less familiar, but you'll hopefully feel comfortable of how all of these things fit together. Okay, so let me motivate the least squares regression problem by, again, going back to the regression task, which is we're trying to find this baseline function f of xi, where it's been corrupted a bit by noise in terms of the observations that we have in hand, the yi's that we have in hand. Now, what I'm going to do for simplicity of the calculation is I'm going to assume the noise is of a very particular form. I'll just assume the noise is a Gaussian with mean 0, and it has variance sigma squared. Okay, so it certainly satisfies those conditions that we needed, which was that the expectation of the noise is 0. Okay, and then let's suppose, again, just to keep life kind of simple, let's suppose that the ground truth function here, f of x, is just a linear model. So it's just this weight, I'll call it w star, transpose times x. So that's all we'll assume for f. It's just a linear model. Okay, so under those assumptions, now what I need to do is I need to find a model h which is learned from some finite collection of data, xi, yi. So inputs and then the noisy outputs. And we're going to learn over the model class of linear models. And so in this case, in theory, with infinite amount of data, we should be able to recover the ground truth function f, because this is a consistent learning problem. In practice, of course, that could be challenging. But okay, so let's work through one strategy by which you might try to recover a model for the observations that you have in hand. And so this is a very powerful kind of paradigm that, again, we're going to see come up in a lot of different contexts, especially when we get into doing unsupervised learning and we talk about things like generative adversarial networks and other types of generative models that are used across machine learning. The idea is, if you have a bunch of data in hand, why not try to model it probabilistically? So in other words, what I could do is I could say, well, let's suppose that I construct a probabilistic model that can kind of reproduce the data that I'm seeing. And let me figure out which one of my probabilistic models kind of most likely reproduces that data, or makes that data, sort of the most likely thing to have appeared. And so this is going to be the strategy of this probabilistic modeling approach. Okay, so what we're going to do is we're going to try to predict the data by doing the following. We have this weight that we can play with, right, in H. And so what we're going to do is we're going to say, okay, well, let's suppose let's suppose I know something about the noise statistic. Let's suppose I actually know the noise statistic has a variance sigma squared. Then what I could do for my choice of weights W is I could generate artificial data, let's call it tilde yi, from an input xi, right? What I would do is I would just take my weight, dot it with xi, add the Gaussian noise with that variance sigma squared, and then out comes my predicted tilde yi. So you can think about now each model H here I have is actually modeling a probability distribution over the data, okay? Parameterized by W in this case. So what are the probability densities that you get in that case? So of course the noise, because it's just a Gaussian with mean zero variance sigma squared, that's just given by this first expression. And then now what I can do is I can use the fact that if you look at the relation between the observation that you would have and what the ground truth model would have been, what the relation on xi would be, I could subtract these two, and that will give me a certain realization of the noise A to I. So what I can do is I can say, well, if this were actually the truth of what the model was that generated the observations, this would be the probability that I would have seen yi as my output. So the probability of seeing yi, given that you had the input xi and the true weight was w, would just be this Gaussian distribution with mean zero and variance sigma squared. So the probability of seeing yi would just be yi minus wtxi, because that's the realization of A to I you would need, divided by 2 sigma squared, exponentially weighted, and now you have that probability. Okay, so the probability of seeing the observation y is given by this expression here. We have it explicit in hand because we've postulated this probabilistic model for how the data was generated. Okay, again, this is not something that requires us to know what the ground truth is. This is simply a model that we're postulating for the data, and our job is going to be to use this to try to discover what W is. Okay, so now if I had the full data set, because we assume every observation is coming at us IID, identically distributed, independent, identically distributed, what we're going to have then for the probability of the whole data set, y1 to ym, given the inputs x1 to xm, for that particular model W, we're going to have just the product of the probabilities, which is given by this expression. Okay, so now you start to see something that's looking a little bit closer to least squares, because if you look up here in the numerator, you see that, oh, that is just the sum of the square of the errors, right? So under this Gaussian model, you see that the probability that you would have seen that data is essentially this Gaussian, where the key term up here is the sum of the square of the errors. And so this term, this collection of products of the probability, in other words, the probability of seeing those outputs, that's known as what the likelihood is for model W given the data. Okay, so I'll just use this notation LWS. That's just the probability that if the model truly was W, then this would be the probability that the data you observed would have arisen. Okay, so then the idea is that we can use this as a criteria for model selection. This is known as the method of maximum likelihood. So the idea is we can try to estimate W star by looking over all of the different models that we have in hand and saying, okay, which model leads the data to be the most likely thing that would have arisen. Okay, so it sounds a little funny because you're kind of doing the problem backwards. You're sort of pick the data first, then sweep over the models and see what the probabilities of the data would be under each of those different models. So it's a little funny, but it turns out that you can prove theorems that tell you that this is a viable way to get estimators. In fact, often very good statistical estimators for some parameter of interest. Okay, so the maximum likelihood method now to estimate W star is going to be to pick the tilde W star, which maximizes the likelihood of the data over all the different models. So we figure out which model would have had this data arise with the greatest probability. And then that's going to be the one we use. And then now if you just unfold this a little bit, you realize, okay, making this as big as possible, the probability, that's the same thing as making this sum as small as possible. And then you say, wait a second, I recognize that. That is precisely the least squares problem. Okay, so the least squares problem actually arises from the maximum likelihood method under these Gaussian assumptions. And so it's probably not a surprise that Gauss was one of the early people to discover the method of least squares, because he was essentially taking an approach similar to what I've motivated here. Okay, so this gives the method of least squares, and this probabilistic idea, you could replace this with other noise models. You could have a Laplacian here or other types of noise distributions, and then this would give you different optimization problems for how to do your model selection. In other words, how to do the regression task, and that would motivate different loss functions that I abstractly framed out in the previous slide. Okay, so that's least squares. We can go one step further, and we can also use a Bayesian motivation in order to try to do our model selection. And this also becomes very powerful to get a whole different range of loss functions. You've probably seen in some contexts things like cross-entropy losses and things that are used to do regression. A lot of those have their origins in this Bayesian perspective. Okay, so let's go through the theoretical strategy that's based on using a Bayesian motivation to select our model in regression. So again, you can go back to that idea that we want to somehow score the probability of seeing certain data under a choice of model. So again, that whole probabilistic model idea we can utilize again. Now what I'm going to do here is I'm going to say, okay, the probability of having seen the outputs y1 to ym, given that the model is w, again, because IID, it'll just be the product of the individual observations. Now, if we had the Gaussian model, as I said before, we would have exactly the expression here, and we'd end up with the likelihood. Okay, so that's what we did before. Now, instead of just using this very let's say unbiased estimate or uninformed estimate of W. In other words, W we're saying could be anything. We could try to exploit Bayes' rule and say, well, maybe we know something about which models are more plausible than other models. Like maybe I know something about what the order of magnitude of W should be. And so what we could do is instead of just using this kind of raw IID expression for saying what the probability of the data is, we could instead use Bayes' rule. And so the idea here would be, let's see if we can utilize this along with Bayes' rule to get a probability distribution over our model's W. And so the ingredients for Bayes' rule, as you know, is the likelihood, which I computed on the previous slide in detail. The prior is what I was just talking about a moment ago. If we're informed in some way about what a plausible model is, we should leverage that if we can. And so Bayes' rule would allow us to do that by having some probability distribution that we specify over the class of models. Like let's suppose we know the weight vectors have to be on the order of 10, right? We don't know if it's 5, we don't know if it's 20, but we know it's not like 3 million. So what we would do is have a Gaussian distribution, for example, that we put over all of the weights where we center the Gaussian around 10 and maybe have a variance, of our standard deviation maybe of 10 or something like that, right? And now all of a sudden, our learning is going to become much more efficient than if we had to hunt over the entire space of weights where they could potentially vary over many orders of magnitude. So Bayesian estimates are often much more efficient, but of course, it all hinges on you having some strong, often prior information about the solution to really benefit from that. Okay, and then the evidence here is nothing more than just a normalization constant. Okay, so if I take this Bayesian strategy, now this is going to get me a distribution over the models that I could use now, again, to motivate various types of solutions to the regression problem. Now, the approach that we'll often take will be to simply choose the model which is most probable under the posterior distribution. And so in this case, what you would get is the following. So this is going to be a case where what I've done is I've taken over the class of models. Well, okay, let me just leave it abstract. I have a prior. I'm going to show you different choices you can make for the prior in a minute. And now what I'm going to do is I'm going to find the model which makes the posterior, which is, let me say this carefully, I'm going to find the model which is the maximum under the posterior distribution. So that's going to be our strategy for doing the model selection now. So if I now work out what that is in a little more detail, that would mean our estimate, tilde W star, is going to be the arg minimum of negative log of the posterior. So because you get these products and so on that appear, it's often useful to not just do the maximum directly, and also because things vary over many orders of magnitude and you get round off errors and so on and overflow errors in your numerics. It's often useful to take the probabilities and take a logarithm of them. And so maximizing the probability would be the same thing as minimizing negative log of the probability. Okay, so now if I do that and I expand out what this logarithm term is, you'll see the first term will essentially be what I had before, which will be the likelihood. And we know that minimizing the likelihood is going to be the same as solving this least squares problem. And then, you know, all these other terms will kind of come out. I guess there'll be a prefactor term here, and that term will just come out as an additive sum. So you can neglect that. And then now what's going to be interesting is there's going to be one more term, which is going to be the prior. That's going to come out as what I've denoted here as lambda r, just chose to organize the term that way. And then you'll have the evidence. But you can see the only things that depend on W are the prior and the likelihood, and this piece of the likelihood. And so I can write out the negative log probability that we need to minimize over. I can throw away all those extra terms, and what I'm left over with is what I've written here. So we have a least squares problem now, but with an additional term that's coming from the prior distribution. And so that additional term, though, is going to play a really, really important role in many regression problems. This is going to serve the role of being a regularizer. And so in this case, you can see if I had prior W, this immediately generates the regularizer R of W, which is given by negative the log of the prior distribution over W. Okay, and then when you kind of collect all the terms together here, the lambda here will be this 2 sigma squared over m, which, you know, is related to the noise there under our probabilistic model. Okay, so that's a way that we can use Bayesian ideas to also arrive at an optimization problem for solving regression tasks. So again, the role of the prior here, let me just give you a specific example. Let's suppose we know something about W, like the order of magnitude. We could model that, or we know that we don't want this thing to go too far away from 0. We could model all of that through some Gaussian distribution. That would be a simple prior to work with. But it doesn't have to be a Gaussian. It could be pretty much any prior that you dream up. Now, if you use a Gaussian, some nice things happen, of course, when you apply the logarithm. And so you'll see that if you use a Gaussian, that we'll get an L2 regularizer in that case. And so, so now RW would have this explicit form of being W squared. And then I can fold the rest of the constants into the lambda. And you'll get then sigma squared over m nu squared. And it'll be a positive value in this case. Okay, so now that would be what happens if we use this Bayesian idea. We not only get the least squares problem, but we get a regularizing term as well. Okay, now what's interesting here is if you notice there's this ratio between whatever the noise was in the data and whatever my prior is here, nu. And so if I were to take nu to go to infinity, that's going to be like having a less and less and less you know, well-informed prior in pinning down the value of W. And so if I take nu going to infinity, then the prior becomes increasingly less informative. And essentially that lambda parameter goes to 0, and the whole thing essentially reverts back to good old-fashioned least squares that we had before. So the way that I like to think about it, and this is why I want to do this derivation, is in some sense least squares is kind of not the ideal way to solve a regression task, because it's almost like saying, I'm just going to fit the data I have in hand, and I know nothing about what the more plausible or plausible models are. So in some sense, least squares is a situation that you really want to try to avoid for all the reasons we've been talking about the last few lectures. Because if you don't have any regularization, you're really you know, setting yourself up to potentially overfit the data by fitting the noise. And so we're going to see that once we add this regularization term, we often can get much better performance and much nicer models for our regression tasks. And you can think about that again as being motivated by this Bayesian perspective. That essentially what we're doing is we're using some type of prior information about what models are sort of more plausible. Okay, so I should just also mention that when you add this regularizing term, especially with this Gaussian prior, this leads to a whole class of regression techniques, which are known as ridge regression methods. And you'll see this will come back and play an important role when we start talking about those different forms of regression I outlined on the previous slide. Okay, so I think I'll end there for now, and then I want to pick up and talk a little bit about how we have to trade off between, again, getting our empirical errors low on our training set versus considerations of how complex our models are. And that'll kind of follow a pattern a little bit similar to classification, but there are also some interesting additional considerations. And then what I want to do from there is then move into talking about some rather specific forms of regression based on some of the ideas I outlined before. You know, so doing kernel ridge regression, doing lasso and some of the connections with compressed sensing and some of the other extensions to the nonlinear setting. Okay, so what we're going to do is mainly focus in the short run on L2 risk, and so basically least squares being our overall loss function. There's no reason why we couldn't use LP in some of the theorems I'll state in that general case, but L2 tends to be the most common place where people will frame their regression problem. Okay, so the idea of L2 risk is that you're going to penalize the model by its deviation from whatever the labels are that you've been given or the output that you've been given in your data set by the square error. And so if you had access to the actual underlying function f, and that's what I'm going to look at here, we're going to basically look at the true generalization error, the true risk. Then you would have for your loss function that L of H, L of F would be the L2 norm between H and F. Typically, we'll only have point evaluations, though, of H of X and F of Xi. Okay, now for the moment, I'm going to look over the hypothesis space of all functions which are measurable with respect to the data distribution. And we'll assume F is also a measurable function. So that's just a technical assumption. I'm basically just saying, let's suppose for the moment we go with completely general hypotheses, and the concepts are basically the largest sort of reasonable class that we could come up with and still be able to do the analysis readily. Okay, so that's the notion of an L2 risk. And now the optimal solution in that case, and this is again in the most idealized setting where we have access to the true risk, then the optimal solution to this problem would be this function, which I'm denoting by M. And what that would be is you go over all measurable functions, and the true risk, right, what you're trying to minimize is the expected loss under the data distribution. Of course, as I've emphasized many times, we don't have access to this in practice, but it's still useful from a theoretical perspective to see kind of what the ideal model would be. Okay, so if we do that, we can say, all right, take the expectation of the L2 loss. What's the best function that matches the data we'd have in hand? And remember, there's potentially noise and so on in the data. Okay, so it turns out that this can be solved analytically, and it turns out that the optimal solution that minimizes the L2 risk is going to be the conditional probability of the outputs y that we've seen, given x was the input little x. And so you'll see this come up in a lot of different contexts. You know, if you know about Kalman filtering and techniques in control, this same exact statement comes up, and the reason is because those techniques are based on estimators ultimately motivated by L2 risk. So, so this conditional probability is the best function in some sense that you could put into your L2 loss that would approximate the function f of x that's obscured by noise. Okay, so that's good to know what the ground truth is in some sense and what the sort of most ideal estimate would be if we had access to all information about, for example, the data distribution and outputs y. Okay, so what we're going to do is we're going to, obviously develop techniques that approximate that idealized setting. But what we're going to see is there's some interesting considerations in going about it and doing that well. So that means that in the case when there's no noise, m of x would recover, perfectly f of x, of course. What we want to do is, of course, look in the case when we're actually doing the traditional sort of regression task where the h we have will typically be more restrictive, and our job will be to pick out for n samples the best model we can, in some sense, mn of x from that hypothesis space. Now, of course, what we want to know is what are going to be the implications of different choices of hypothesis spaces and different estimators. Okay, in the sample set, I'll just denote here by S sub n for n samples now going from 1 to n. I wanted to use the notation m because m of x kind of is like a mean. And so this is kind of like the mean of the random variable y given x. So that's the notation for using m here. Okay, so now what we can do is something really interesting with this. We talked about how different models will behave as you draw different samples. That was referred to as the variance, and I'll give a very precise definition of that in 1 minute. We talked about how, on average, your model, how close it is to the underlying concept, and that was referred to as the bias. And what you're going to see is if you were to take this L2 risk and you start to play around with the complexity of the model class, what you would see is that And this is the generalization error, by the way, that I'm plotting in red here and the vertical axis. You know, at first, as the model went from being, let's say, something very simplistic like a line to, you know, maybe you do this with polynomials. You know, you start with a line, then you go to a quadratic, cubic, and so on. You would find that, oh, my, you know, generalization error is getting better and better and better. You would hit some sweet spot where all of a sudden, after you start making the model more and more complex for a fixed number of samples, you basically start overfitting the data, and your generalization errors will actually start to become bad. And in fact, they'll kind of diverge to become really bad if you keep going with the complexity of your H, because essentially what it'll do is it'll just memorize the training data, and there's really no interesting you know, features that it's utilizing that can generalize once it starts to see new inputs. So this red curve is just, you know, showing you what the generalization error would be if you selected a model based on a finite amount of data, as the complexity of the model class H kind of goes to infinity in some sense. Okay, now I did mention with deep learning and training protocols and so on, you can get this double depth behavior and so on. But let me start with the most basic bias-variance trade-off theory, and then we can talk about those things when we get into those subject areas. Okay, so I hope everybody understands what this diagram means at an intuitive level. And now what I want to do is give you the detailed mathematics of how you can get a feel for where this sweet spot is, at least theoretically. So the idea is we're going to start off looking at the error having chosen the function mn from our hypothesis space. So remember, the sort of, you know, best estimate that you could have gotten is m of x, which is this conditional expectation. So now the L2 error is just going to be given by the expectation under the data distribution of whatever the model is that you selected and whatever the best approximation would be for this input-output relationship, which is m of x, as I showed above. Okay, so now what we can start to do is we can do a little bit of analysis here where we square out this term, and that will, of course, give me the expression that I've shown here on the right. And then what we can do is start to rearrange these terms, and we're going to find something interesting when we rearrange the terms. In particular, what we have is this m of x and mn of x. If I take the expectation over mn of x, we'll get that. The m of x, it does not depend on anything related to the samples that were chosen, so there's no randomness there. And so, so that can be taken outside the expectations. Okay, now what I'm basically going to do is I'm going to add and subtract this m of x expectation term. So expectation of mn squared, I'm going to add and subtract that in this expression. And if I add and subtract those terms, I will get this expression that you're seeing there. Now, you may wonder, why am I doing that? The reason why I'm doing that is I'd like to have a term which is broken off that basically depends on how much the mean value that you would get of mn of x is relative to what m of x itself is. So the expectations here, by the way, are being taken over different samples chosen from the data distribution. Okay, so let me just make that very clear that, you know, imagine we draw a sample, we select a model from H. That's what mn is. Then we draw another sample, we'll get another function m sub n. We draw another sample, we'll get another function m sub n. So these expectations are all over how the model is going to vary based on the finite sample that you happen to get randomly. Okay, so now we see something really nice happens, which is by doing this little trick of adding and subtracting this expectation of mn squared, I can look at one of these terms as being a variance, namely these first two terms I can collect together, and that gives you the variance of the models as you draw different random samples, what you would have predicted at the location x. And in the second term, if you look closely at it, basically what that is that's very similar to the L2 least squares error. This is basically saying, let's take the average that you would have predicted over all the different models that you got and compare that to what m of x is. And so that'll be what's called the bias. For those of you that know about statistics, right, an unbiased estimator would be one where this expectation would be equal to m of x. But, you know, the model selection procedure is very general here. And so there's no a priori reason why the models have to average and give you the correct underlying mx. Okay, so I can just, you know, again, shorten the notation a little bit by taking this error term, and we call that the bias motivated by what I just mentioned about statistical estimators. And this last term then is the bias of our estimator squared. And the first term is, again, the variance. And so this is, again, all relative to how the models are going to vary as I draw different random samples of size m. Okay, so now this diagram really helps us understand why, as we increase the model complexity, our generalization errors can become potentially bad, and that there's going to be kind of a, where there might be potentially a sweet spot between these two effects. So basically the bias-variance trade-off is as follows. If you just think about the benefits of increasing the complexity of your model class, in other words, let's just again use polynomials. So we'd have linear approximation, quadratics, cubics, and so on. As we increase the degree of the polynomials, we can fit richer and richer functions. And so if the underlying function m of x is some continuous function, the bias term is going to continue to go down and down and down. It's going to decay as we increase the degree, right? And so that seems like a good thing on the surface of it, because we have really rich representational capacity. But as I mentioned a moment ago, there's a downside to that, which is that the data is going to be obscured by noise. And so there becomes a really important issue of trading off representing what the underlying ground truth function f was versus simply fitting the noise that you memorizing your training set. And so that's where this trade-off is coming in, and that's what this bias variance trade-off is really capturing. Because what happens now is, let's suppose you got the bias really, really tiny. So you're using a really high degree polynomial. Let's say it's even degree n+1. So I can get the bias down to 0 at least on my training set. There's a problem though. As soon as I go and I grab a new random collection of samples, now what happens is the model fits that perfectly. And then when I grab another one, it fits that one perfectly. So what that means is that there's going to be huge fluctuations in the underlying model prediction at location X, because every time it gets a new set of samples that have new noise, it's just fitting it, exactly. And so that would mean that you would have a really large variance term. And so as you can see, the L2 loss is going to be a sum of the bias squared plus the variance. And so even if I get the bias to 0, I still have to worry about this variance term. And as models become more and more complex, their variance tends to increase. And so that's why we get this, this behavior here on the right arm of this red curve. So again, the whole challenge is to find a model which is sort of getting the essential information out of the training set while not under or overfitting it. And that's going to get you the best predictions. So basically, if you're on this arm to the right, you'd be overfitting. And if you're on this arm to the left, then it means, oh, maybe your variance is pretty small. You could benefit by increasing the complexity of the model. But as I mentioned, there's going to be some sweet spot where that trade-off kind of balances out. And that's what I'm denoting here. Okay, so I'll pause there for a minute, but this is really essential in order to be able to get generalization from your underlying training set in the context of regression. And so this analysis really captures that key set of ideas. Okay, so that's the bias variance trade-off, really, really important. And even neural networks, even though there's this double dip, what's really going on in that context is there's additional regularization where in some sense you are controlling the model complexity. So you're not fully overcoming this issue. It's just that the issue is manifest in a little bit more subtle form than given by this particular setup. And that's because the loss functions that I'm looking at here don't really include the role of regularizers and things of that nature yet. Okay, so really important for generalization that you balance model complexity so you don't overfit or underfit your training set. Okay, so that's how this plays out for the regression tasks. Okay, so now there's another issue that also is really important to really have in the back of your mind when you're working on regression tasks, which is to think about the dimensionality of the space on which you're trying to approximate a function. And so again, this is going to come down to an issue of trying to figure out what the essential features are, that is the essential information that is contained in your training set that you can leverage for the purposes of building a model and ultimately achieving generalization. So the curse of dimensionality is something you may have heard about in other contexts in numerical analysis. And so I just want to show you that even in the context of machine learning, this is very much something you do have to worry about. Okay, so let's do a rather simple calculation where we're going to sample points at random on the unit cube. And so, obviously data distributions can potentially be more complicated than that, and also have structure where things live on a manifold and so on. And we'll be discussing that in some of the future lectures. But let's just say that the intrinsic dimension associated with your data is d-dimensional. And so let's use as our prototype kind of data distribution, uniform distribution on the unit cube. Okay, so what we're going to do is we're going to draw samples x, and then we'll draw samples x1 through xn. And then what I'm going to do is I'm going to look at basically for that sample x, how close it is to other samples in the sample set. Okay, so this would be an example just sampling uniformly on the unit square. And then what we'd have is this measure for basically how close points are together. Because if you think about trying to leverage something like smoothness as a way to get generalization in your regression problem, then you have to have enough points nearby the point x so that you have enough information to make a sensible prediction there. And so what we'd like to do is try to get a lower bound or on how many data points in some sense we need so that it fills up the space enough that we actually have a chance of making predictions at locations x that maybe we haven't seen before. Okay, so what we're going to do is use this statistical quantity, which I refer to as the minimal sampling distance. And the idea is that if you give me n samples chosen randomly, and you give me that point x that was chosen randomly, I'm going to ask, what is the distance to the closest point in the sample of n points? Okay, so in terms of our diagram, imagine x is this particular random point that we drew, and then we say, okay, what is the closest point to me? Well, it's that one right there. What was that distance? Okay. Now, of course, all of this is random because the location x that you're choosing and the samples are chosen randomly on the unit cube. So we'll just take the expectation of that. So we'll kind of do that experiment over and over and over again, and we'll say, okay, on average, how close are points nearby? And what we're ultimately going to want to do is characterize this in terms of the dimensionality of the space that we're in and the number of sample points n that we've utilized. In some sense, this is telling you how well the samples are filling out the space. Okay, so we can now express this in terms of a probability distribution pretty straightforwardly. Whenever you have an expectation of something that has some value, you can integrate over the probabilities of that value being greater than or equal to some cutoff, in this case t. And so if I integrate this from 0 to infinity dt, this will be the same thing as the expectation, because you're going to overlap with the value of t, t times in some sense. Okay, so this allows me to characterize the minimum sampling distance in terms of a nice integral, and then I'm going to introduce some approximations. Okay, so one of the nice things to do is to say, what's the probability of being greater than t? That's 1 minus the probability of being less than or equal to t. And then what I'm going to do is I'm going to look at a particular choice of the norm. In this case, we're going to use the infinity norm. So when I'm talking about that distance, I'm going to look at all of the component distances and take the maximum of those, right? That's the usual infinity norm that we use in analysis. And so what we're going to have here is that the probability of the infinity norm being less than or equal to t, if you just kind of think about it for a minute, that would be the probability that each sample, when you drew it, at least one of those was less than or equal to t. And so if you just think about the sort of geometry of this, if I'm less than or equal to t, it means that x and x minus xi had to land basically in a little interval of length at most 2t. Okay, and then I do this n times, and so this gets me an upper bound on the probability that that distance is less than or equal to t. Okay, and the d there is because we're in d dimensions, so that gives us the volume of that little region. Okay, so now what I can do is I can use this to get a lower bound, because what I can do now is I can say, well, it was an integral from 0 to infinity, 1 minus this probability, let me do the integral over a smaller range. In this case, I'm going to do it to this range, and you'll see why I do that in a minute. Let me use this bound on, let me use this upper bound on this probability. And because I'm doing 1 minus something which is upper bounded will give me a lower bound. And so then what I can do is I can actually get an expression to lower bound the minimum sample distance given d and n by this expression here on the right. So it's just a little calculus. You just integrate that out, and this is what you get. Okay, now what's significant about this, the prefactor, is interesting. It's d over 2, d plus 1, but you can see as d kind of gets to be large, that's going to approach basically 1/2. The more interesting part is the scaling in d, which means I'm going to have a lower bound here on the sample distance, which scales like n to the -1 over d. Okay, so that's interesting because that tells me as d gets bigger and bigger, how quickly the minimum sample distance at best could decay to 0. Okay, so let me give you some numbers so you really get a feel for this and really what the issue is when we go to any appreciable dimension d. So in 1 dimension, which is just the interval basically, that's the one-dimensional cube. In that case, if I have n samples, you can see that the lower bound decays really, really rapidly, right? I get negligible lower bound for 100,000 samples. But as I go up in dimension, 2, 3, 4, and so on, up to 10 dimensions, you can see that this n to the -1 over d decays very slowly. And so, with 100 samples, you have a lower bound of 0.28. Even with 100,000 samples, so 100,000 data points, you're still going to have a minimum sampling distance that is at least 0.14. And the situation gets even worse when I go to 20 dimensions, as you can see here. Even with 100,000 samples, I still am not even lower than I'm barely lower than the case of 10 dimensions in the case of 100 samples. So I mean, it's really going very, very slowly, and the situation just gets worse and worse as you go up in dimension. So again, this really points out that when we're successful at machine learning tasks, we're probably not successful simply by relying on notions of smoothness in our regression task. There's some other structure, mathematical structure that has to be utilized when you get into higher dimensional spaces. In some cases, the higher dimensional spaces, features that you get will superficially be high dimensional, but there may actually be a low dimensional structure there. And that's when we start talking about unsupervised learning techniques. That's where those techniques are going to be really interesting in helping us tease out that low dimensional structure so that we can help avoid things like this curse of dimensionality. This is kind of the issue of, for example, using like raw input images. If you use a raw, 1920 by 1080, set of pixel values, and you're just trying to use smoothness to do some type of classification or regression task, the situation's kind of hopeless. And this curse of dimensionality calculation, I think, gives you some insight into why. So typically what you have to do is extract some collection of features on which then you're going to either do regression or classification so that you can get down into a sensible intrinsic dimensionality. But again, this is mainly exploiting the notion of smoothness for the sake of regression. Of course, other considerations come into play if your machine learning algorithms use other types of structure. Okay, so when you're just relying on smoothness, be very careful about the dimensionality of the problem that you're working with, because you will need a tremendous amount of data once the dimensionality even becomes fairly modest, like 10 or 20 dimensions. Okay, so just this scaling of n to the -1 over d should be in the back of your mind when you're doing regression tasks and how big the sample size is that you're attempting to use. Okay, and again, this kind of points out what I said the last few lectures. To really be successful in many machine learning tasks, you really have to exploit some type of intrinsic mathematical structure in the data. Okay, good. All right, so let's talk a little bit about how we can start to characterize the generalization properties of regression. Okay, so if you remember in the past lectures, we found one nice way to characterize the complexity of the hypothesis space was to use notions of Rademacher complexity. And we can similarly do that in the case of regression tasks. So what we're going to do here is we're going to consider the case when our hypothesis space is such that the difference between h of x and f of x is at most some bound m. That way we don't have to deal with sort of unbounded errors. And so in practice, you typically can do that. And then we're going to have some input space X. We're going to have a concept space as before. That's going to be our ground truth function f of x. And what we'd like to do is characterize, if we make a choice of a specific hypothesis space, in some sense, what's going to be the connection between the empirical risk that we're observing, that's usually the thing we're using as part of our training, and what the underlying true risk is. And so the following bound is really fundamental for that. If we use the LP risk, what this says is that the expected error under the LP risk, under the data distribution, is always going to be bounded by the empirical LP risk that we see. This is the error that we see over our training set, plus 2p m raised to the p minus 1 times the Rademacher complexity of whatever hypothesis space we chose, plus a sampling term which scales in this way. So this last term, it's very similar to what we've seen before. The main twist here is if you use the p norm and you have errors at most size m, it'll scale like m to the p there. But really, these first two terms are the ones that are typically most of interest, because these are the things we have a lot more control over. Okay, and then you can do a version of this where you use the empirical Rademacher complexity, and that's very similar to the previous bound. You just get some additional factors here in the sampling confidence term. Okay, so this is kind of like the fundamental theorem to use if you want to characterize for a specific hypothesis class that connection between the empirical risk and the true underlying generalization error that you would expect to see. So this could be helpful, for example, in your design of hypothesis spaces and understanding how much data is really going to be needed in order to do effective training in that context. Okay, so that's something that now generalizes some of the results that we had seen in the case of the classification tasks. So a lot of our job then is going to be to figure out clever ways that we can try to do model selection or create a hypothesis space so that this Rademacher complexity term is small, balanced against trying to get the empirical risk small, right? In some sense, this term is what the error would look like on our training set. Again, if we make H really, really rich, we can get this value small, but we'll pay a price here in terms of the Rademacher term. So it's always a balance between those two, and that's going to lead to different optimization problems and motivate a few different forms of regression. Okay, so the complexity of the hypothesis space needs to be balanced against the the ability to achieve obviously low empirical risk on our training set in order to get a nice bound on the generalization error. Okay, so that's going to be our key strategy, and I'm going to show you how you can do this for a few different hypothesis spaces, and it'll motivate some interesting things related to, again, how you might do model selection and formulate optimization problems for regression. Okay, so what I need to do, if we want to take, or at least have in our tool, collection of tools, an approach similar to the Vapnik-Chervenankis dimension, I need to do a little bit of an extension for the case when we're trying to do regression tasks, because we don't really have the same notion of shattering when the output is a continuous variable y instead of a discrete collection. So, so this is just to show that you can take this combinatorial approach to get bounds similar in spirit to the Vapnik-Chervenankis dimension, to characterize, obviously, the complexity of the hypothesis space H. Okay, so the basic idea here is going to be to extend our notion of shattering. So what we're going to do is we're going to take a bunch of sample points, x1 to xm, and we're going to say they're going to be shattered if there exists a bunch of these values, t1, t2 to tm, so that you can get the cardinality of these classifiers, these binary classifiers, that it's the number of labels that it assigns is basically the full collection that you could assign, which is going to give you cardinality 2 to the m. So this is kind of like the growth function. The one little twist here is we're going to characterize the complexity of G by using it as basically a decision function, so that it will give us a positive value when the label should be 1 and a negative value when the label should be -1. And what we're not going to require at each sample point that we be able to get the full range of Gs. We have these values T1 to Tm, which can allow us to shift the function up and down. So we just need to have that it's rich enough that as we go over different choices of G, we can realize all the different label sets given a fixed collection of these thresholding values, T1 to Tm. Okay, I'll show a picture of it in a minute, I think, which will also help make this concept clear of how we generalize the notion of shattering to a collection of functions that we want to use for regression. Okay, so we're going to call these values T1 to Tm. We'll call those the witness of the shattering. And so this is really what's going on. So let's suppose you had your class here, G, and it had these four functions in it, right? This blue function, this green function, this red function, and this purple function. Now, of course, what we need to do in order for this to have an analog of VC dimension being 4, we'll call this the pseudo dimension, we need to be able to assign all possible labels here at these 2 points. I guess this would actually have a pseudo dimension of 2, right? Because we want to realize all of the labels -1, 1, 1, -1, 1, 1, -1, -1, right? Those are the 4 labels if you had a pseudo dimension of 2. And so the idea here is we have these 4 functions to work with. If I choose at x1 the first witness value to be this one that I've drawn here, T1, and the second one, T2, to be there, you can see that now if you give me any assignment of labels, let's say you pick +1, -1, I can find a function in my model class to realize those labels in this, in this way. So in other words, the green function is going to give a +1 at x1 because it's above the witness, and it'll give a -1 at x2 because it's below the witness T2. Okay, and so you can see here that this collection of functions is rich enough to realize all the different possible labels over 2 samples, but probably not rich enough to do it, for example, over 3. Okay, so basically the largest number of samples for which you can find witnesses and you can realize the full collection of label sets, then that'll be called the pseudo dimension of the function class. Okay, so it's playing a role very similar to the Rademacher complexity, just with that little modification of having these witness thresholds. Okay, and that's going to be very useful because then we can start to make generalization bounds very similar to how we utilize the VC dimension and so on. Okay, and so you can kind of look at the pseudo dimension in some sense as being the VC dimension of the collection of classifiers that you would get if you basically allowed for all different choices of these witness variables. So it's closely related to the VC dimension. Okay, so now here, if you go and you want to do, let's say classification, sorry, not classification, but regression now, using hyperplanes to fit your data, we can go, and it's not too hard to show that because of this connection with the VC dimension, the pseudo dimension of the class of hyperplanes of dimension n will again be n+1. Now, the reason why that's useful is because this is saying that the pseudo dimension of linear regression is going to be n+1. And so that immediately then allows us to get a very nice combinatorial bound on the generalization error. And we'll show in a little bit that we can do even better. We can get tighter bounds, but this becomes a really nice way to understand how much data you need to get reliable linear regression. So I'll just pause there for a second if there are any questions about the pseudo dimension and connections with the VC dimensions. Okay, so now here's the generalization bound that comes out of using just purely combinatorial considerations over your hypothesis space. So now if you can compute the pseudo dimension of the function class that you want to use, then the generalization bounds are of this form. So this means then that the empirical risk will bound above the true risk by m times this expression involving the pseudo dimension, very similar to what we had if you go back and look when we use VC dimension, plus this sampling confidence term. So the class G, of course, that we're going to characterize using pseudo dimension is not the hypothesis space itself, but it will be the collection of loss functions that come out of this choice of hypothesis space. Similar in spirit to what we did when we were looking at the VC dimension. And then there are lemmas that we could also establish that will link together the hypothesis space with the pseudo dimension directly on H. But this is typically the way it's done because different loss functions will exhibit slightly different pseudo dimensions. Okay, so this is very useful because it basically tells you the amount of data you need. It has to be proportional or bigger than the pseudo dimension of the model class that you're working with. Okay, so that gives the analogous result to the VC dimension, and now we have a rigorous way to get an estimate, at least on the ballpark, of how much data we need to have a hope of having good generalization of our models. In other words, that the kind of training errors that we're seeing are indicative of what probably the true test errors would be if we deployed our model in practice. Okay, and again, you can see that there's some favoring, in some sense, having lower complexity models that would have smaller pseudo dimension, provided you can still attain good empirical risk. Okay, so for the hyperplanes, then the model would be finding weights W, so that when you give an input X, and also finding the value B, so that you have a hyperplane approximating the data. And we're going to see this is probably the most common form of regression that you'll encounter, because if you combine this with a kernel trick, you can use this even for nonlinear data sets. Okay. So, all right, so these are bounds, again, I just want to emphasize that are when your primary strategy to do regression is to minimize empirical risk. We're going to see in a little bit that you actually can do better than these bounds if you incorporate into your objective function some type of regularizer, and we'll be doing that in a little bit. Okay, so that's kind of the fundamental theorem for regression when you're, again, using empirical risk minimization as your primary training strategy. And now this gives you a nice handle on how much data you need in order for your models to generalize well. Okay, so let me talk now about linear regression in a little bit more detail and get us a little bit closer to how you would carry all this out in practice. And we'll see the generalization bounds become a really useful motivator for different practical methods for addressing the regression task. So again, if we go back to the linear regression problem, and I've kernelized it here, so it's actually going to apply as well to some nonlinear problems if you pull back from the feature space. Now, what we can do is we can reformulate this in a few different ways that'll be helpful for purposes of optimization theory. So the first thing to realize is this is a convex problem, and something that we can actually solve directly. We don't need to do any really fancy optimization algorithms to get the weights W. Okay, so what I'm going to do is reformulate this problem in terms of some nice linear algebra. In particular, I'm going to collect together all of the evaluations of the input data into this big matrix X. It's sometimes called the data matrix. For now, I'll organize everything in these columns, and then I'm going to add an extra feature, which is 1. And that way I can get rid of having to track a separate variable for the bias. And then I'm going to have this weight vector, which will just be W1 to W capital N, where capital N is the dimensionality of the feature space. And then because of that additional feature I tacked on, the bias would then be the last weight. Okay, and then Y will just be the outputs that we're trying to ultimately predict. And these are the ones that we've gotten from our training set. Okay, so if we put all that together, then we can actually write this, this summation in terms of this matrix product. And then you could think of the norm here as being the usual Frobenius norm. Okay, so if you work all that out, this is just a reformulation of what I had up there. But what's nice about it is now I can try to solve this optimization problem by just directly computing the gradient of this. It's just a nice little quadratic form that I have. And so if I go and I do that, I claim the solution will be this. It'll be XX transpose inverse XY. And I'll tell you what the dagger means in a minute, because sometimes this won't be invertible and we'll have to do something a little bit special to handle that. Okay, but this really gets us towards practical algorithms for actually computing these various types of kernelized and, well, I'll tell you what the kernel is in a minute, but these various forms of regression. Okay. So here's the gradient of f. Setting that to 0 would give you the minimizer of this quadratic. Again, we're trying to find the weights W. And so if you just do a little linear algebra, you'll find that this whole thing comes out to be this expression 2 over m x transpose W minus y. Got to set that to 0. You can see now where that XX transpose is going to come into play. So put that together, collect all the terms involving W on one side, Y on the other side, and you get this. And then now if I go through and I work it out, I get X transpose inverse, X transpose Y. Okay, so it looks, and then the idea is though, if this XX transpose is not invertible, then we're kind of stuck. So what we're going to do is introduce this notion of the pseudo-inverse. Instead of doing a direct inverse, we're going to use what's called the pseudo-inverse. And the idea of the pseudo-inverse is out of all the solutions W that I could put into this linear algebra problem, let me take the one, in other words, if I have a null space, let me take the one that basically yields a W with the smallest L2 norm. And if I do that, that will distinguish a particular solution, even when the matrix XX transpose is singular. Okay, so the basic idea of the pseudo-inverse, if I had a general matrix A, is as follows. I could define an inverse by solving, let me just write the solution down and I'll point back to this limit. If I had the problem AX equals B, even if A is singular, I still can distinguish the solution X. Of course, I'm making some additional assumptions in order to distinguish a particular X, but I still could define some notion of X that approximately solves AX equals B. The idea is this follows. Let's suppose that A is singular. Well, what I could do is I could say, well, let's try to make the residual between AX and B as small as possible in the L2 norm. Now, of course, that's not going to uniquely distinguish an X because there may be a null space for A. So there might be many, many X's that give me exactly the same quality residuals here. So what I'm going to do is I'm going to tack on this additional term, which says don't just make the residuals small, but also make the L2 norm of the X vector itself small. So I'll have gamma, which will tell me how strongly I should pay attention to making the L2 norm of X small. Now what I do is I basically solve this problem. I'm going to call that X gamma. And if you take the limit as the gamma parameter goes to 0, the X that you get out, I claim, is going to be given by this pseudo-inverse. Okay, so if you just work out the linear algebra here of this minimization problem, you'll find that the linear algebra actually gives you this problem that I put inside the limit. So X transpose A plus gamma I, that would be the left-hand side if I just took the gradient in X of this minimization problem. And then the A transpose would be hitting the B term. And so when I put it all together, I would basically have this operator A gamma, which would be A transpose A plus gamma inverse A transpose. And then now what I want to do is I just want to pick the solution as we take the gamma parameter going to 0. If I do that, that gives me this special solution operator A. Now, of course, in the case when the A itself was invertible, it turns out A dagger will be the same thing as A inverse. Okay, so this is what's known as the Moore-Penrose pseudo-inverse. Okay, so that's very useful because it allows me to solve the linear algebra problem, at least with some approximation, even in a case when the matrix A is singular. So very, very useful technique. This is just a quick overview of kind of standard least squares regression. All right, so what I can do with this, and a few other interesting things. This also motivates why we need to do the pseudo-inverse. And so let me show you a specific example where we have an XX transpose that is nearly singular. And this is often what happens in practice. So the pseudo-inverse, or even using the gamma, can also be useful in cases when the matrix is kind of ill-conditioned. So it may not technically be singular, but it may have very, very disparate eigenvalues, or what numerical analysts would call very ill-conditioned. And so this pseudo-inverse can kind of be a nice way to work around that issue, or even using a finite gamma, as we'll see in a little bit when we do ridge regression. Okay, so results obviously can be really sensitive to noise when this XX transpose is very singular. Okay, so let me show you how this plays out in practice. So this would be a great scenario where we'd want to do linear regression. So the data is nice and scattered, and it really samples well over both of our features, feature 1 and feature 2 here. So no problem finding a nice hyperplane, in this case a plane, that fits the data. Okay, now this is often the way that data presents to us in practice. So you see what's going on here is, technically there are 2 features, but there's almost no real wide sampling in the feature 2. It's almost all concentrated just on one value for feature 2. So in that case, it's going to be very, very hard to distinguish between models, because any small perturbation out of that, that little feature 2 plane is going to lead to a totally different slope for the hyperplane that's fitting the data. In other words, the plane that I'm showing you is just as good as the one that tilts the other way or even in other directions, as long as it just captures the trend. Let's see if I can play it again here. Along the feature 1 vector, it's going to have a small loss function. And that's typically the scenario we're in. And that can occur for a number of reasons. Could be you just didn't sample enough, but it also could just be that the features that you used, you didn't scale them to be a comparable order of magnitude. And there's all kinds of other things that could be arising. So, all right, so that's typically the scenario you're in. And so if you do the pseudo inverse, what that fixes for you is when there's a direction where you don't have a lot of information or data, it essentially zeroes out that direction. And so the key difference between the middle and the right here is the plane now that I'm fitting with the pseudo inverse, because it doesn't have any information in the variations in feature 2. It essentially just says, okay, we're not going to use feature 2 in making our prediction of the output. And so it'll set the weights on feature 2 to be 0. And so all the weights will essentially be on feature 1. And as I mentioned a moment ago, often when we do linear regression, we are interested, obviously, in making the final predictions, but we're also interested in the weights, because the weights will often tell us how influential or important different features are to the final prediction that's being made. And so you can think about the pseudo inverse as a way of saying whenever weights can be expendable, let's set those to be 0. And that way, the final interpretation that we have of our model is much more reflective of the correlations between the input features and the output. This middle one would be very misleading, because you could potentially have a very big weight on a feature which really, at the end of the day, plays very little role in making an accurate prediction. Okay, so that's another motivation for why, when you do linear regression, you really want to use the pseudo inverse, even if you can find some other workarounds. Really is better to have this model selected as opposed to the one in the middle. Okay, so this motivates also this idea of kernel ridge regression. So in the standard regression, I showed you this pseudo inverse. That was the limit of taking the weight to be 0. There's no reason why we couldn't keep that weight finite, and we'll see that that has certain benefits. So let me motivate this from the point of view of the regression bounds, or the generalization bounds that we've been proving, because this really, again, illustrates how, if you really think about the full generalization bound, not just the empirical risk in isolation, you often can get much better performance out of your methods. And so what we're doing here is we're going to consider regression now over the class of planes. But now what we're going to do is we're going to constrain the weights in the L2 norm to be less than or equal to lambda. And so you remember when we did support vector machines, that was actually one of the big motivations for the objective function that we obtained at the end, was to try to make the weights small while at the same time correctly classifying. And it's the same idea here, which is try to fit the data well while at the same time making the weights small. And we're going to see that those types of models will often have much better generalization properties than models that just kind of try to regress over the entire class of planes. Okay, so now what we're going to do is we're going to make this assumption on the models, and this capital lambda will be kind of like a hyperparameter that we would tune later, and we'll see from the optimization perspective that basically will come in as an additional penalty term when you kind of do your primal and dual formulation. And then we're going to make a few little assumptions, which is for the kernel, we're going to characterize kind of the largest the data can be in the feature space. So that comes in terms of the kernel. We'll assume that kxx is less than or equal to r squared. That's just so that everything lives in a ball, so it doesn't go off to infinity, more for technical reasons. And so most practical scenarios, this won't be too restrictive. Okay, but r squared will characterize how big the data is. And then we're going to also make the assumption that the ground truth function that we're looking for similarly doesn't kind of diverge or too quickly. So for all the x inputs that we'll have, we'll assume that it's less than or equal to lambda r. Okay, so under those technical assumptions, what we're going to have for our generalization bound is the following. So this is now making more use of the structural information related to H. It's not a purely combinatorial bound like we had when we used the pseudo dimensions. So this actually will perform better in practice in predicting the connection between our training error and our true risk. Okay, so the bound says basically that the true risk will be bounded by the empirical risk plus something proportional to the square of the norm of the weights and something proportional to the square of how big the feature vectors are. But really the square of the weights are going to be the interesting term here. And of course that all of this will scale like 1 over the square root of m in the sample size. So you can use this in some sense if you had estimates of these quantities of how much data you would need, so that again your training error is indicative of what the generalization performance would look like. There's a slight refinement that you can do on this bound, which also allows you to express this in terms of the kernel. And so now instead of having this this term 1 here, you can actually get a term that involves the square root of the trace of the kernel operator. So it's just kind of summing over all the xis, and then this decays like a square root. Okay, and so the second bound will be a little tighter than the first one, but it requires some deeper analysis of or at least knowledge of the properties of the kernel, in particular here the trace of the kernel. Okay, so that's going to be much better than the pseudo dimension. And really what it motivates is trying to develop regression models that in some sense have small weights. And you can see that that lines up very nicely with what we've already said about the pseudo dimension and it selecting models which are more generalizable in some sense. Okay, so one objective or approach that you could use to obtain an objective function would be to try to minimize not just the empirical risk, which would be the least squares error, but try to balance that against this complexity term. So in other words, try to balance empirical risk against also making the weight small. And if you do that, that's going to lead you to ridge regression. And of course, if you kernelize everything, hence kernel ridge regression. So the idea of kernel ridge regression is not just to make empirical risk small, which is what the standard least squares problem was, but also to try to make this lambda squared term small as well. And so you can do a little rearranging up here, and what you'll find is that the upper bound can be expressed like this, where the term on the L2 norm of W would have this specific form for lambda. But the key idea is replace your objective function with this explicit regularizer to balance these two terms, and therefore you'll have better generalization performance. Okay, so that's the abstract motivation for ridge regression. Now let's talk a little bit about how you deal with the actual optimization problem that you get out of that, which is shown here on the lower right. So now instead of just solving the least squares error small, you're going to balance that against this regularizer that the norm of W is small. Okay, so that's the basic problem that we need to solve, and we need practical methods to do that. And so we're going to develop some optimization strategies. And so here we go. So this is the notation I had before in terms of x, the weight vector y, just kind of is nicer than writing out these sums. Let me just give you sort of an intuitive understanding of what the key difference is between what we were doing a minute ago with ordinary least squares. If we were to look at this in terms of level sets of the objective functions, so each of the curves here you could think of as being the level sets of a least squares problem. If I solve for least squares, I'm basically just finding that point right there. And that's perfectly fine on some level. But as I showed you before, if my data is not rich enough in certain dimensions or directions, that model can be somewhat misleading if I try to interpret the weights, or not have as good a generalization performance as the model that had the sort of level slope, slope 0 in the directions that it didn't have any information about. That model will perform much better if all of a sudden we start introducing inputs that start to have a feature to dependence. So the idea of ridge regression is you're going to perform what's called shrinkage. You're going to basically solve not only this ordinary least squares problem, but also try to make a minimum of this L2 regularization term. And if you kind of combine these two together, you can see that the minimum then would move from being that point there to the one that I have here. Okay, so that's the idea of the ridge regression, is you're going to try to balance minimizing this beige objective function, which is the usual least squares, against the L2 regularization term. And so it leads to this kind of shrinkage towards the origin, which, as I showed you before, can be beneficial in certain ways because it might eliminate some of the weight components, for example. Okay, so that's the formulation mathematically, and it's good to write it in terms of this vector notation. And if we do that, then we can apply the same analysis that I did before, which is we can solve this outright because it's still a quadratic form. And now you see, again, that expression XX transpose plus lambda I coming up. And now this is the linear algebra problem that you would solve for ridge regression. Okay, so pretty straightforward to handle numerically once you kind of organize things the right way. Okay, and then now we can kernelize this, as I mentioned before, by replacing our inner products in X with K, and now the weight vector would be this K. Actually, this would not be the pseudo-inverse now. Now you would do this K plus I L inverse and then K of XY. So pretty straightforward to generalize what we did before to the kernelized case. And then now you have a really nice viable technique that can work even in fairly large dimensions using this kernel trick. Okay, so the idea is that, and I'll talk about kernels in a future lecture, the idea is that we can address this issue of dimensionality by having good notions of similarity between data points, xi and xj. So we'll see again in future lectures how you might develop such kernels, either through handcrafted ideas about what the relevant features are, or using deep learning, such as things like convolutional neural networks to try to extract feature vectors from things like images. Okay, so that's kernel ridge regression and the mathematics of how you would solve that and kernelize. Maybe I'll pause there for just 1 minute if there's any questions about that. Okay, so now what we're going to do is I'm going to show you how to look at this from the point of view of the dual, and that's going to be helpful for further formulation of some of the other regression techniques that I was mentioning before, in particular the support vector regression and some of the other ones. Okay, so as I mentioned a moment ago, you can look at this primal problem equivalent to a constraint optimization problem where this lambda here would be a data derived constraint. So there's a link here between the little lambda and the capital lambda given the collection of data mathematically. So you can always solve the primal, for any solution of the primal problem, there's always an equivalent solution in terms of a constrained primal problem of this form. And that makes the connection with the generalization bounds I was telling you about before. Now you can also go one step further, which is we can introduce slack variables, and that's often useful when you want to do a dual formulation. And so instead of looking at the primal variables as being W, what we could do is we could introduce slack variables xz, which is basically the residuals, and then the primal variables become the residuals and the weights. And so it'd still be subject to the constraint that I had here, and the fact that xzi would now have to be equal to yi minus w dot phi of xi. And we're going to see this is going to be useful when we start doing the dual formulations and applying things like the KKT conditions in order to get nice representation theorems for our solutions. Okay, so kernelization then, we'll see that come in a little bit. It's really natural to motivate from the point of view of the dual formulation. Okay, so now if I have the Lagrangian using the slack variables, then you see the Lagrangian is going to be the sum of the squares of the residuals plus the constraints. Alpha I prime here now will not need to be non-negative. It'll just be any real number because we have, in some sense, two inequality constraints, right? That would give you the equivalent of one equality constraint. And then we have the constraint on the weight size that's given here by this parameter lambda. Okay, so now if this is my Lagrangian, I can work through the optimization theory to get the dual formulation for the optimization problem. And that's going to be very insightful, as I mentioned, into how the final solution is represented in terms of kernels. If you remember, right, we showed that you can write down the linear algebra using kernels, but you still have that weight function times phi that you would need to deal with in order to make predictions of your final regression. I'm going to show you that by using the dual formulation, actually I can even eliminate this w dot phi term and work directly in terms of a linear combination of kernel evaluations. Okay, so that's one of the motivations for doing this this dual calculation. Okay, so the idea then is, I can now write this down using the KKT conditions, and I'll get the following in terms of the weights. The gradient of the Lagrangian is going to be given by this expression, and the utility of this expression again is it gives me a really nice representation of the solution to the primal problem. So what this tells me is that the weight vector is going to be some linear combination of these phi of xi, these feature function evaluations. And you're going to see that now if I dot w with phi, what do you notice, right? So if I'm summing over here from I equals 1 to m, and I want to evaluate this at, let's say, xj, that would simply be a dot product between phi of xi and phi of xj. And now what you can do is replace that by a kernel, and you would never have to work in the feature space. And so you'll see that come back in a minute. And that's all derived from the first KKT condition. Okay, so it's a nice representation formula for the solution. The residuals now give us another little representation formula for alpha I. It turns out to be 2 times the residual. So that kind of gives you a little interpretation of the alpha I terms, that they're essentially the residual. And then there's the consistency conditions. This is quite interesting because this now tells you that the alpha i's will only be non-zero when this exactly goes through this point here. Okay, and then the last one, of course, the consistency condition tells you that either the norm w is lambda squared or lambda is non-zero. So those are very useful conditions often when you're trying to do practical calculations with these regression setups. Okay, so this is going to then be the dual formulation. Now that we have representation for w and xz here, we plug that into the Lagrangian, and that gives us our dual function. It's equivalent to having minimized over w and xz. We just use calculus to do that up here. And then now we get this expression for the dual function. And I'll finish up in a few minutes. So we get this expression for the dual function. It really is just a bunch of exercise in algebra. If you plug into the expression up here for xzi squared, the alpha I prime over 2, that gets me the first term here. If I expand out this sum, that's what got me the second term. Plugging in the xz again got me the third term. And now you see the w, if I plug in the sum for w, that got me the fourth term here, which involves, notice, a phi of xi dotted phi of xj. And then similarly plugging in for lambda, the norm of w squared gets me the last term here. So, it's pretty straightforward. It's just a little bit of algebra to do those substitutions carefully. Now I'm going to rearrange this a little bit by introducing this notation alpha I, which will be alpha I prime over 2 lambda. And so if I do that, I can rewrite the first term in this way. When I combine it with the other terms, I get a negative sign out front. The second term comes from doing the substitution. This term and the first term are combined. That's where I got the negative. The summation comes out from the phi of xi, phi of xj term. And then this all simplifies. This term and this come together to give me that. And simplifies to just negative lambda, capital lambda squared. Okay, so again, it's just a little bit of algebra to arrive at that. Okay, so now the utility of all of this is this gives me the dual formulation now of the optimization problem. And I'll finish on this, which is now what we're going to do is maximize over an arbitrary unconstrained alpha the following function. Negative lambda alpha transpose alpha, 2 alpha y minus alpha transpose conjugated with x transpose x. So this looks very similar to the linear algebra problem that I had derived from the primal problem. The utility of this, though, is this only involves now the kernel, because this x transpose x is basically phi of xi, phi of xj, if you look at the ij entry. And so now this basically tells me what the linear algebra is to solve for the kernelized problem. It's k plus lambda I. Inverting that I will get me the solution. Okay, so the bottom line is you do this derivation in order to get that the weights can be expressed completely in terms of the kernel. And ultimately, I can even dispense with having to compute w dot phi of xi, because if we use the representation formula for w, we realize that the whole thing boils down to a linear combination of kernel evaluations. Okay, so the utility of doing this calculation is I can completely kernelize the method not only in the linear algebra to find the coefficients, but also in expressing the form of the final functional form of the regression model. And so, so that's really great, because then you can completely dispense with having to work in feature space, which means then we can start to use things like infinite-dimensional feature spaces, and we're really just reducing the entire problem down to kernel evaluations. Okay, so I'll end there for today, and then I want to go through some practical demonstrations of these techniques next time, and then move us towards doing neural networks. So thanks for joining us today.